Okay, this is a video to step you through what you need to do for your moon observing project. So on Friday, May 1st, you were emailed several documents. One of them is what's on the screen right here, the instructions for the moon report. And the first page of those instructions contains a step-by-step roadmap for completing the assignment. And in particular, the steps are lettered in order here, and they're also referenced to step 2 on page 3, step 3, page 4. So you can use that as a sort of a shortcut to speed things up. But essentially what you're going to do is report the recorded information that you stored from the dailymoonposition.com website on the Blackboard survey into a spreadsheet, and then you're going to analyze your data. So just as an example, here I have one of my own moon photographs that was taken on January 29th, right at the start of the semester, 5 p.m. at Hofstra's campus in Uniondale. So you can either collect up all of your photos and get the data you need to put into the spreadsheet by using the dailymoonposition.com website a second time, or you can follow the instructions that I sent you for retrieving the information from the Blackboard survey using the My Grades tool. I can't show you that because Blackboard doesn't let me behave as a student. When I click on the My Grades tool, it just tells me, you're the instructor, you don't have grades. But if you click on the My Grades tool, the first time you click on it, you get a table of all of the Blackboard assignments. One of them will be the moon survey, record a moon observation survey. Click on that, and that should give you a table of all of the different times that you've taken the moon observation survey. And then you just want to click on each one of those and keep clicking on any link you get on a new page until you finally get sort of a grade summary report, which will show you your answers for that single time that you took the survey. But if that doesn't work well, you can always just start with your original photo like I have here. Open it up in your phone, in your laptop photo viewer, and it should summarize the date and the time and the location for you. And so then you can just go to the dailymoonposition.com website and simulate that information. So if we interesting. All right, well, so you just want to always be sure to set your zip code reasonably accurately. If you're anywhere in Nassau County and New York City, Suffolk County, Hofstra's zip code 11549 will work. It's not that critical. Just as long as you're within a few dozen miles of where the photograph was really taken. Set the date, and then set the time, remembering that this website uses military time, so afternoon times you need to add 12 to the time. So this photograph was taken at 5 p.m., so we select 17, military 1700 hours is 5 p.m., and it was taken right at 5 p.m., so I set the minutes to 0, and then I ask it to update. And now it is simulated that crescent moon for me. It tells me that the crescent moon was 22% illuminated. It was in its waxing crescent phase. It was at an altitude of 43 degrees above the horizon, and its azimuth, what we want to record as the red number, was 206, and on this dial 0 is north, 90 is east, 180 is south, 270 is west. So I could say that that was either south or southwest. Let's call it southwest. So I want to record this information in the Excel spreadsheet that I've sent you. So if we click to the Excel spreadsheet, let me pull up the blank one. Here we go. So I've opened Moon Report Spring 20 blank underscore Mac. And here I've got the spreadsheet. You want to expand it and make it large enough so that it's mostly filling your screen. You want to be able to see starting from column A all the way over to column N in one screen. And in this spreadsheet, the top part, this table with the yellow cells, is where you will enter your data. And then as you enter your data, it will automatically get plotted in these 3 lower plots. There's plot number 1 here, plot number 2 here, and finally plot number 3. And as you enter your data, more new information will be plotted on in these plots. So right when you open the spreadsheet, the first thing you want to do is personalize it for yourself. The spreadsheet is made to be as foolproof as possible, as safeguarded against errors as possible. So the only cells that you can change, you as the user, as the student user, are the yellow highlighted cells. So if I click on a white cell, it will allow me to select that cell, but it will not allow me to change that cell. If I try to type in it, I get an error alert saying, the cell you're trying to change is on a protected sheet. To make a change, you need the password. So that's a safeguard to prevent you from inadvertently messing up the spreadsheet. So just keep in mind that the only cells you can change, the only ones you can enter information into, are the yellow highlighted cells. And so you want to put in your first name and your last name and the date in which you're going to submit your final report, so you can update this later, but let's say we're going to submit it on the 8th. And edit your section in. So if you were in the 220 section on Tuesdays and Thursdays, that's section 1L. So let's enter that to be 1L. All right. So you've personalized it with your name and your section. And now that first observation for the photo that I was showing you. So here's my photo again. So it's taken on January 29th at 5 p.m. So I want to put the date in 1/29/20. Just use the exact same format as the first 3 rows here give you as an example. You'll notice that as soon as I put in a date there, this observation number counter started counting for me, and my last name and my section showed up over here automatically. And this was at 5 p.m. So 5 p.m. This is one of the more frustrating things about Excel with its time format, is that it's very, very finicky. I need to enter the AM and PM as capital letters without periods. If I just type in 5 and lazily hit return, it's going to assume 5 a.m., which would be incorrect. If I type 5 P period M period, it doesn't understand that that's a time. And so if either the date has a typographical error in it or the time has a typographical error in it, This column over here, column N, will say value, hashtag value. And these columns will say hashtag values. They're error flags that I've programmed in there for you so that you'll know you've got a typo in your date and your data won't plot correctly. So if you see one of these lines with the value error messages in them, go back and hunt down and figure out what your typo is. In this case, get rid of the periods in 5 p.m. And now it works correctly. And then I want to enter the rest of the information from my photo from the Blackboard survey. What was the condition of the sky? Was it daytime? Was it nighttime? Was it twilight? As we can see in my picture, it was twilight. The sun is down, but the sky is not dark nighttime sky yet. So I can enter twilight. It was taken at Hofstra. The sky was obviously clear in the photo. So if you recorded all of this information originally, you can get it from your Blackboard survey. If you didn't, reconstruct it as best you can from your photograph. And then from simulating it on the dailymoonposition.com website, we see that I was looking to the southwest at an altitude of 43 degrees, and the Blackboard survey tells me that I should record that as southwest, and that 43 degrees would be medium high in our bind. Very low, medium low. Very low is below 20 degrees. Medium low is between 20 and 40. Medium high is between 40 and 60. Greater than 60 is very high. And that's obviously a crescent moon. And the dailymoonposition.com website tells me it's in the waxing phase. And it reported that it was 22%. We want to round these the percent illuminations to the nearest 5%. So is this closer to 20% or is it closer to 25%? It's closer to 20%. So we want to put 20 in there. All right, so I've got all the yellow cells filled in for this first observation on this date and at this time. Observing under these circumstances, the moon was presenting me with a waxing crescent phase, 20% illuminated. As you enter your date and your time in the correct formats, Excel will calculate this number over here in column N. It's going to calculate how many days have passed since midnight at the very start of December 31st in 2019. And the reason for that, choosing that date, December 31st of 2019, is that you'll see that I've got an observation up here taken on January 2nd. I've got an observation taken on January 10th. I've got an observation taken on January 17th. If I take this date and this time and ask how many days accurate to a fraction, to a decimal day, have passed since the very start of the very first second of December 31st of 2019, I would find that 11:45 p.m. on January 2nd, well, almost 3 days have passed. And 4:55 p.m. on January 10th, 10 3/4 days have passed, roughly. On January 17th, earlier in the morning, 17.33 days have passed. And so what the spreadsheet is going to calculate for you here is how many days in January have taken place. So late on January 2nd, I get a value of 2.99. Late on January 10th, I get a value of 10.7. Early on January 17th, I get a value of 17.33. If I were to put in January 31st at 12:01 a.m., if I don't get Watch out for typos. There we go. All right, so 1 minute into January 31st, it calculates it as 31 days into January. So this is just going to give us a nice linear progressive time scale. It's just going to be this the number of days into 2020. That's the way to think of it. What's the day number in 2020 of your observation accurate to 1/100th of a day? And so this is just going to get calculated automatically for you. It automatically takes into account daylight savings time. So in entering your dates here, just enter them exactly as your clock recorded them, the clock on your phone. If it's April 1st and you took an observation at 6 p.m. Eastern Daylight Time, record it as 6 p.m. here, and this will account for the hour shift of daylight savings time. So this is going to be one continuous time scale, always in standard time, and it's going to it's just going to keep counting days into the year, days as if January never ended. So you can see that if we put February 1st in there, February 1st is the 32nd day of the year because there are 31 days in January. So February 1st is the 32nd day of the year. And March 1st in 2020, February was a leap year, so we had 29 days. So 29 days in February, 31 days in January. We see that March 1st turns into the 61st day of the year, because the 29th of January would have been the 60th day of the year. So you just want to sequentially go step by step in chronological order and enter all of this data for each one of your moon observation photos. However many you have, put them in here in date order. If you find that you've made a mistake and you want to eliminate something, let's just quickly put in garbage values. So I've just put in some garbage values there. I want to get rid of this row entirely. It was wrong. I put it in the wrong date order, whatever reason. I want to get rid of it. I do not want to use the delete function in here. I want to clear this data, and I just want to clear the contents. And so, boom, it's gone. Alternatively, I can click on a cell and then just use the backspace key, the delete key, to get rid of information. But I don't want to cut or paste rows. I don't want to select a whole row and delete it by cutting it, because then the rows will want to shift. So just don't do that. Either use the edit clear contents command or use a backspace key. Alternatively, you could take a bunch of blank cells and copy them and then paste them in their place. And that's another efficient way to clear out data. All right, so I'm going to take a shortcut here and copy over a bunch of my own observations of the moon. This is a subsampling of my data set. And I'm just going to cut and paste them into here. And so now I've got 18 observations of the moon spread from the earliest one on January 29th to the latest one on April 28th. And now that they're all in there, I see that the day numbers just progressively get larger and larger and larger. April 28th was the 119th day of 2020. And once all of your data is entered, then you can scroll down here and look at plot number 1. Plot number 1 is conveniently titled Your Moon Data in Spring of 2020. So your data. And what we see is that the very first 3 data points up here that are in white and that you can't edit or change, early dates in January, January 2nd, January 10th, January 17th. That was when the moon went through its first quarter, full, and third quarter phases in January. Those data points are plotted on this plot as these 3 green circles here in January. So what we're plotting in this plot is the percent illumination of the moon on the vertical axis. The moon can be as small as 0% in its new phase to 100% in its full phase. And the scale runs from -10 to 120 to give us a little bit of blank space above and below our plot. And then the horizontal axis in this graph is our days past 12/31/2019. It's the time scale in column N here. So I'm just going to take the percent illumination of each observation and the day number of each observation, and I'm going to plot a point for each one of those. For these first 3 observations up here in white, those are plotted as green points, green data points. The green data points are data that I'm sharing with you. Your personal data points from the percent illuminations here in yellow with their corresponding day numbers will be plotted as red data points with error bars. We rounded to the nearest 5%, so we've got 5% error bars. This data point was recorded as 85%, but that means it could have been as large as just below 87 or just above 82.5. So we want to give it a plus or minus 5 error bar. No measurement is ever perfectly accurate. Every measurement always has some uncertainty with it. And so we need to graphically visualize that uncertainty with these vertical error bars. The time uncertainty is extremely small. Your phone records things accurate to a minute, and so the horizontal error bars, the horizontal uncertainty in time, is much, much, much smaller than the circles that we're using to plot, so we don't need horizontal error bars. All right, and so we can see that across the semester, sometimes the moon had very small percent illuminations and was in its crescent phases. Other times it was full, right up at 100%. I personally caught it 1, 2, 3, 4, 5, 6 times where it was so close to full that it rounded to 100%. A couple of gibbous observations in here, and a couple very close to quarter. This one was at 55%. This one was at 45%. And the gray vertical lines are the first of each month. So the gray vertical line at day number 1 is January 1st. At day number 32 is February 1st. At day 61 is March 1st. At day 92 is April 1st. And at day 122 will be May 1st. You can see that in most systems, Apple and Microsoft, as you roll your cursor over elements on the graph, you get that little pop-up text box telling you information about it. And so in particular here, we see that these gray, by rolling my cursor over the gray line, I'm rolling over the series of data that I labeled month dividers. And in parentheses there, you see the coordinates. The x coordinate is 92.0 for the first day of April. That's day 92. The first day of May is day 122. The first day of March is day 61. But the bars there just help you visualize the individual months during the semester: January, February, March, April, and May. And now what we want to do is fit a mathematical function to our data. This is what scientists do. We take data, we take observations, and then we look for patterns in those observations. And we can kind of clearly see that the moon's phases go from small values up to 100% illumination and then drop back down to 0% illumination and then climb back up to 100% illumination and then drop back down to 0 illumination and then climb back up to 100% illumination. So we can fit a mathematical function to that, and that's what this solid blue line is. Programmed into the spreadsheet is a sine curve, a trigonometric sine curve. You might remember this from a high school trigonometry class. If I draw a circle on a page on an XY plane and then let a point move around the outer edge of that circle at a constant rate, at a constant turning rate, then the Y position of that dot, the vertical position of the dot, will be the trigonometric sine function, and the horizontal position of that point rolling around a circle is the cosine function. And because circles are symmetric, the cosine function and the sine function look very similar to each other. They're just shifted versions of each other. So Excel programmed into this plot is a sine curve. And if I want to draw a sine curve, we kind of covered this back in our lecture on light. If I want to draw an oscillating sine curve, I need to know three things. I need to know the height of the peak and the depths of the troughs. That would be the equivalent to percent illumination in this graph. And because it's the moon can be in its new phase or its full phase. It can be 0% illuminated if we're looking at the nighttime side. It can be 100% illuminated if we're looking directly at the daytime side. So the amplitude ranges from 0 to 100, about an average of 50. So it can be plus 50 above 50, minus 50 below 50, ranging from 0 to 100. So that's the amplitude. The other thing we need to know is the period of the oscillation. How frequently does the pattern repeat itself? And so that's our horizontal time scale. How many days does it take the moon to go from one new moon to the next new moon? That would be the period of the moon's phases, the synodic period of the moon's phases. So we would need to know that number in order to plot a sine curve representing the moon's phases. And then the third thing we would need to know is where to start. And so we need what's called a phase 0 point, a 0 point to start our curve at. And in this plot, I've given you two little yellow cells up here at the upper right. And the top cell is the day number of the new moon. Ooh, that should say the new moon in January. Sorry. Crap. I will email you a new version of this, of the spreadsheets. But it's the day number of the new moon in January. So looking at the behavior of the moon's phases, I can see it was at a quarter phase. It then went up to its full phase about 7 days later. And then about 7 days after that, it was back down to its quarter phase. So this is the first quarter, the full moon, the third quarter moon. The new moon must be somewhere around the 25th because it's now climbing back up through waxing crescents, going back up to the next full moon. If the full moon in January was on the 11th, then about 14 days later is when I would expect the new moon to take place. So I'm going to continue to demonstrate this website, or this spreadsheet for you, but I'm not going to show you the right answers. So I'm going to switch over to a different version where I've adjusted the calculation a little bit of the days past calculation so that it'll let me demonstrate the spreadsheet, but it won't give you the right answer here in this video. So I'm gonna enter all of my data in there. I'm going to so we're seeing the same data as before. I've emphasized up here that these values are not correct. Do not copy them directly into your spreadsheet when you're working with your data. You want to fit this blue curve to your data. But so we need to make an initial guess. Whenever we're trying to establish a pattern using math, scientists start with reasonable guesses. And so every month of the year has a new moon in it. And so if I had to make a wild random guess at where the new moon was in January, a good guess would be to put it the 15th, put it in the middle of January. And our months, our calendar months, which are either 30 or 31 days long, are based on the cycles of the moon. Originally, the original Jewish calendar, the original Chinese calendar, the original Arabic calendar, these are all lunar calendars, and the months are defined strictly by the phases of the moon. Our modern Western civil calendar started as a lunar calendar, but then evolved and broke free of the lunar cycle and just came with fixed dates from then on. But the original fact that our days, our months, are roughly 30 days long came from the moon's orbital period. So we know that the moon's orbital period is somewhere not as long as 31 days. Most months have either 30 or 31 days. So, well, a reasonable guess then would be 30.5 days for the period of the moon. So you want to enter 15 and 30.5 up here. And once I hit return, the spreadsheet will now plot the a sine curve with these parameters. It starts at the 15th of January. There's my phase 0 point. This blue diamond is my phase 0 point. I've asked it to be on the 15th of January. And I'm going to shrink this just a little bit. There we go, so we can see the whole thing at once. So there I can see the whole plot all at once now. So we're starting on the 15th of January, and I will return to the new moon 30.5 days later, and 30.5 days later, 30.5 days later, 30.5 days later, so that after 1, 2, 3, 4 months, starting on the 15th of January, the new moon in May is around day 137, which is 137 minus 122, 121, sorry. 137 minus 121. So that's on May 16th. Since February only had 29 days, it didn't get as far ahead as we might have expected it to, but it has gotten, it's not just 30 days, 30 days, 30 days, 30 days ahead. It's not 120 days ahead. It gained a half a day there, a half a day there, a half a day there, a half a day there. So it's 122 days ahead of January 15th. And our goal is to adjust these two numbers such that I make this blue sine curve hit these data points really, really well, very as accurately as I can. And so, as we've already seen, if the full moon is here, and this is the first quarter moon, and that's the third quarter moon, then my new moon belongs down here. So I need to increase my my 0-point day number. And I'm guessing that it needs to be around 25. So let's just start a little bit shy of that. Let's put it to 23. Okay, I'm getting this blue curve, the hump, the peak of the blue curve is approaching my full moon, and it's approaching both of the quarter moons, but it's always to the left of them. So I need to make this number larger. So let's try 25. Still need to go a little bit bigger. Let's try 27. Ooh, we're getting close now. So I see that I've got the blue line going dead center through that green point. It gets pretty good through that green point, but it's to the left of that green point. So I want to keep going up, but now in smaller increments. So let's try 27.5. That's looking good. To set the day number in January, you want to use your data points that are immediately to the right of it in the first few weeks of February, and these 3 green data points. And you want to get the blue curve to match them as best you can. And so right now, I'm doing pretty good. I'm getting the full moon point here well. I'm a little bit to the left of the center of that green point, but I'm also a little bit to the right of the center of this green point. And so I'm splitting the difference. I'm sort of balancing them out. The curve is a little early for this point, but it's a little late for this point, so it evens out. And I'm going through those 2 points well. I'm going through those points decently. So I'm pretty close with my z value, but now I see that as I let my curve run through the rest of my red points, I'm to the right, I'm to the right, I go through that one, I go through that one, I'm to the right, I'm to the right, I'm to the right, I'm to the right of those 2, I go through that third one, I'm to the right, I'm to the right. And so that suggests like this 30.5 number is too large. So I want to shrink it. I want to take this coiled spring of my blue sine curve and I want to squeeze it so that I want to compress it, meaning I want the period to be slightly smaller. So I could try 30 and see what happens. All right, so my fit over here is still decent, but now as I go across, I'm to the left, I'm to the right, I'm to the left, I'm to the left. I hit those well, I'm to the right, I'm to the left. Looking at all of this, I might want to tweak it up a little bit. Let's try 30.2. And let's try 30.1. All right, so this is what I would consider to be a fairly decent fit, in the sense that my blue line is touching every single one of the red data points. It goes within the error bars of all of the data points. And in particular, these first 3 green data points, which I have shared with you and I have triple checked for accuracy, it does a good job of fitting them. And so use these first 6 data points or so, the 3 green ones and your first few red ones, use those to get your value of z as accurate as you can. And then once you have that set, use these final data points in April and May to give yourself the most accurate value you can for the period. And once you get the period to work well, if we put it to 30.2, let's look at that. So now I'm hitting that final point dead on, but I'm missing that one a little bit. I'm really just tweaking the error bar there. And similarly there. So I'm going to go back. I'm going to put it back to 30.1. Oops. Did I? And then I could try, does it look better with, say, 27.7? Or 27.3? I just want to keep adjusting these two values now, 27.3 and maybe 30.2. Let's see what that looks like. All right, so, you just want to get your best impression of fitting your red data points and those 3 green data points, getting it as accurate a value, good as a fit as you can. Get that blue line to touch as many of your data points as you can. If you have a data point that looks flaky, I'm going to go up here and let's say I had made a typo entering that value. Oop, not enough of a typo. Let's say I had put it at 95 instead of 45. If you have a data point that is just clearly anomalous, everybody else is matching the blue sine curve pretty well, and this guy isn't, then you want to find it. So by hovering my cursor over this data point, I see that its x coordinate is 110. And so I can roll up here into my table, find the data point with an x coordinate of 110, and then the percent illumination isn't behaving correctly. So I want to carefully look and see the 2 places where the potential errors could be was that I had made a typo in entering the date, a typo entering the time of day, or I made a typo with the percent illumination. One of these 3 things is wrong because this data point isn't behaving the way it should. And so look for typos, correct them, go back to your original photo and confirm the date and the time. And if the date and the time are correct here in your spreadsheet, then go back to the dailymoonposition.com website, simulate that date and that time in your zip code, and get the correct percent illumination. You may have the percent illumination correct, but you have a typo in the date and the time. One or the 2 could be wrong. All right, so once you've gotten a good fit for your own data, then the next step in the project is to do the same task to fit a blue sine curve, but to do it to everybody's data. So in this plot, in plot number 2, the red dots are your data, the green dots are your professor's data, and the yellow dots are all of your classmates collectively, you and all of your classmates' data. And so we want to do the same simulation, and basically you can, as a shortcut, you can start with the numbers that you just took from here. So we can copy those and paste those into here and just decide, is this the best fit, or can I tweak it a little bit? Would it be better at 27.5 maybe and 30.1 perhaps? And actually I do like that better. It does a better job at getting these 2 yellow points in May. So you can see that not every data point is hitting the line, but most of them are. And the blue line is getting within the error bars of everybody. And so if in either plot, in this plot up here or this plot down here, if you've got a red data point that is substantially out of place, there's a typo somewhere. So go back up and fix it. All right, so one thing that this task allows a scientist to do, I've got a bunch of observational data about the universe. I've fit a mathematical function to it, And so now I can use that mathematical function to make observations that I either didn't take or couldn't take. And so I mentioned earlier that the Jewish calendar, the Arabic calendar, the Chinese calendar, these are lunar calendars, and all three of these cultures decided that the first of the month, the first minute of the first day of every month would be at the moment that the moon goes through its new phase. But you can't see the new phase of the moon. So how do you determine it? Well, you take a bunch of observations of the moon in its waning phases, you take a bunch of observations of the moon in its waxing phases, and you triangulate where the minimum was, where the 0 point has to be. Based on this continuous repeating pattern of the moon's phases, you can take data before a new moon and data after a new moon and use it to figure out the exact time of the unobservable new moon. And once you've done this for several years, you can then establish the pattern very accurately so that then you can predict when the future new moons are going to happen, even though you won't be able to see them. And so one of your tasks, once you fit your data, once you have your values here set to give you the best fit to your own personal data, one of your tasks is to determine the exact date and time of the new moon in March. And so this purple dot here, this purple diamond, represents the March new moon, the second new moon after our January new moon. And again, rolling your cursor over the plot gives you the x coordinate. I can, if I keep rolling around in here, I'll eventually see Ceres March new moon, and I see that the coordinate is 87.7. The x coordinate is 87.7. Or I can hover my cursor over that vertical purple line that drops down from the purple diamond, and that also shows me that the x coordinate, the time coordinate, is 87.7 days. This is 87.7 days after this day, or I'm sorry, after our starting date of January. The new moon in March is happening on the 87th day of 2020, and 3/4 of the way into it, 0.7 days into it. And if your computer, for some reason, isn't showing you these little pop-up windows, you can still estimate this pretty accurately. What you want to do is go up to the very top of your screen, and in the top menu, I can't show you it here on my screen, but in the top menu is a view command in Excel. And when I click on the view command, I get this zoom menu item. I click on the zoom menu item, and I can increase my view up to 300%. So now I've got this really huge view, really zoomed in view of my graph, and I can come down here and look at my purple diamond and see where the purple line drops down. And I see that that's day 85, that's day 86, that's day 87, there's day 90, day 89, the tick mark for 88 is just there outside my purple line. So the center of my purple line is definitely bigger than 87.5, but smaller than 88, so 87.7. And once I've gotten that, I can go back up to my view menu, go back to my zoom menu, and go back down to a reasonable size for my zoom factor. So finding a value in between data points that you already have is what we call interpolation. And so you're going to use your blue sine curve fit to your personal data in plot number 1 to interpolate the date of the March new moon. Okay, so the other thing that scientists do besides interpolating between earlier data and later data to recover measurements that they couldn't make is we extrapolate into the future. And so once you've done your best fit to the combined class data, so again, you just want to repeat the fitting procedure so that you get these first 3 green points really, really well fit. And the final data points in May, late April and May, very well fit. That will then generally get you a very good fit for the data points in between, and any anomalous red data points, you need to go back up and look for typos in your data entry, resimulate them based on the date and the time of your photo, and make sure that the date and time and percent illumination is correct. And as I'm emphasizing there with a little not correct, these numbers are not the numbers that you will get from fitting the class data in your version of the spreadsheet. I have intentionally tweaked the data so that it has a different period and different starting point. But once you have a good fit to the combined class data, you can sorry for the interruption. Once you've produced a good fit to the combined class data, you can use the blue sine curve to make predictions about the future. And in particular, the assignment has you predict the phase and visibility of the moon on Saturday evening, May 16th. In a normal non-COVID year, this would be the night before Hofstra's commencement ceremony. So if you yourself are a senior, or if your friends are seniors, you might be out celebrating your impending graduation the next morning. And so we can use our blue sine curve fit to predict the phase of the moon. And so given my fit here, I would say that the moon was in its waning phases and was more than 50% illuminated. So it is a waning gibbous moon on this date. And so hovering my cursor over the purple magenta diamond there, I see that the graduation eve point occurs at day 139. That's May 16th, or May 17th, since it's so close to midnight. And the percent illumination, the second number there, the x-coordinate is 139, the y-coordinate is 64.2. So my current fit produces a prediction that the phase of the moon on May 16th will be 64% illuminated, a waning gibbous moon. And then you have to answer a question as to whether or not a moon with the phase that you're predicting would be visible at midnight if it were to be clear. And then the final task of the project is to use this well-constrained sine curve to make a prediction much further into the future. Namely, here we're plotting the sine curve and constraining it with our collective class observations of the phases of the moon across the months of January to May in 2020. If you scroll down to plot number 3, we now go to November, December, and January of 2020 and January of 2021. And as we learned back in chapter 2, every calendar year there are 2 eclipse seasons when the line of nodes of the moon's orbit, the line joining the 2 points in the tilted orbit of the moon, where the moon's orbit crosses the Earth's orbital plane, when the line of nodes points at the sun, that's one of the 2 conditions you need to get either a solar eclipse or a lunar eclipse. And so this red point here on day 347 is the date in December when the line of nodes of the moon's orbit will point directly at the sun. And if you get a full moon or a new moon 17 days before that or 17 days after that point, then you're guaranteed to have some form of eclipse. So the parameter settings that you set in plot 2 using the collective class data to constrain the sine curve is now projected forward into the future 6 months out to December of 2020, and you're going to use this curve to predict how many and what type of eclipses are going to happen during this eclipse season. So the only way you can have an eclipse is if the moon is either in its new or its full phase, and if it's at a node point crossing the ecliptic. And to get the new phase at a node point means that the line of nodes must be pointed near the sun. And so any new moon that falls after this red line here, the start of the December eclipse season, and before this red line here, the end of the December eclipse season, will be guaranteed to give you some kind of an eclipse. So given my data settings here, I would predict that this full moon happens before the start of the eclipse season, so I'm not going to get a lunar eclipse there. This new moon, the 11th new moon, after our 0th new moon here, so 0, 1, 2, 3rd new moon, 4th new moon, 11th new moon. The 11th new moon falls outside of the eclipse season, so that's not going to produce an eclipse. This full moon here does occur within the eclipse season, so it's going to give us some kind of lunar eclipse. This new moon here falls inside the eclipse season, so we would predict that it would give us some kind of solar eclipse. And then the next new moon, the next full moon, the 12th full moon after the start of our project, is outside the eclipse season, so we're not going to get an eclipse there. The moon will miss the Earth's shadow. Here, the shadow of the moon will fall on the Earth. Some part of the moon's shadow will fall on the Earth. The moon will enter the Earth's shadow. The moon's shadow will just barely miss the Earth on this event here. So our prediction is that we will have a lunar eclipse on this date in December and a solar eclipse on this date in December. But we can be more precise than that. Whichever full moon or new moon falls closest to the center of the eclipse season, that's going to be our best, most well-aligned shadow alignment. That's going to give us the best eclipse. And so looking at the green line here for the 11th new moon, we see that that falls on day 343. This is the center of the eclipse season, falls on day 347. So there's a difference of 4 days there. And 347 to this next new moon falls on 358. So 347 to 358, this is 11 days later. So this full moon is much closer to the center of the eclipse season than this new moon. So our prediction would be that we're going to get a total lunar eclipse on this date, followed by a partial solar eclipse, a less well-aligned eclipse, a partial solar eclipse on this date. Now again, I have manipulated the data so that this isn't accurate to what really took place this semester. So your values are different. So your eclipse predictions will be different. However, at least one pair of these new moons and full moons will fall between these two red lines. If you've entered accurate data and done your fits well, either the 11th new moon, the 11th full moon, the 12th new moon, or the 12th full moon will be in the eclipse season, and it's guaranteed that at least one new moon and one full moon will fall in the eclipse season. The eclipse season is 34 days long. The period of the moon's orbit is less than that, so you definitely are going to get the start and the middle within the 34-day stretch of the eclipse season. And just to give you an example, I'm going to intentionally mess up my period, so it's not providing a good fit here, but just to give you an example. Well, that's too much of a change. Let's change it to 28. Okay, so now if our fit in plot 2 had produced this prediction for the future, we would see that this full moon falls outside the eclipse season, so it is not going to give us an eclipse. This new moon does. It will give us a solar eclipse. This full moon does. It's going to give us a lunar eclipse. And then this next new moon does not, so no eclipse. So no eclipse, no eclipse, solar eclipse, lunar eclipse, no eclipse, no eclipse. If we look at the distances, this new moon is now closer to the center than this full moon here. So 341 to 347, that's 6 days away. 347 to 355, that's 8 point some days away. So we would assume that this is going to give us a well-aligned solar eclipse, and this is going to be a partial lunar eclipse. And of our well-aligned solar eclipses, we have two choices. It could be an annular solar eclipse or a total solar eclipse. And we can also determine which one of those it will be by looking at where the moon is in its elliptical orbit. If it's closer than average to the Earth, then it'll look bigger than normal and give us a total solar eclipse. If it's in the part of its orbit that takes it further away from the Earth than average, then the moon will look smaller than the sun, and it will give us the ring-shaped annular eclipse. Along the blue sine curve here, I'm marking the points where the moon is closest to the Earth. Those are the open circles. So at this point around first quarter, the moon is near the first quarter moon in November is when the moon is closest to the Earth at its perigee point. And then during the waning gibbous phases at the end of November, that's when it's closest to the Earth. Furthest from the Earth, Apogee means far from the Earth, and the squares, the open squares, represent the apogee points. So given my current settings here, we would predict that the first quarter moon is going to be near the perigee point. This waning gibbous moon is going to be near the apogee point furthest from the Earth. This solar eclipse is going to happen closer to the perigee point than it does to the apogee point. The apogee point is at 331 The new moon is at 341, so that's a gap of 10 days. The perigee point is at 347, so that's only a gap of 6 days. So this new moon is closer to perigee than it is to apogee, and it's closest to the center of the eclipse season. So we would predict, given the current settings, that the eclipse season at the end of 2020 is going to have a total solar eclipse with the new moon nearer its perigee point than its apogee point. And that will be followed then 14 days later by a partial lunar eclipse. This one will be well aligned and total because it's closer to the center. This one will be a partial lunar eclipse because it's further from the center. And so the instructions list all the possibilities, but it just comes down to which new and full moons. I can tweak this just a little bit more. Let me give this 28.8. 28.9. So, given my current settings now, I would predict that this full moon is inside the eclipse season, but very close to one edge. So, it's going to be a partial or maybe even a penumbral lunar eclipse. This new moon is now very close to the center, and it's very close to the perigee point, so I'm definitely going to get a total solar eclipse at the center of my eclipse season. And then that's going to be followed by a third eclipse in this eclipse season, another partial lunar eclipse. So if the timing is right, if I get a full moon or a new moon really close to the center of the eclipse season, I can also squeeze in the opposite phase, 2 full moons and 1 new moon in this eclipse season, giving me 2 partial lunar eclipses and 1 well-aligned solar eclipse. And because the solar eclipse is happening with the new moon close to the perigee point, it's going to be a total solar eclipse. Let's see if I can give you another example. Let's put this to 30.5. So here, in this scenario now, I've got a full moon very close to the center, so this is going to give me a total lunar eclipse, preceded by a partial solar eclipse and followed by a partial solar eclipse. Let's give myself just a little bit more. All right, so let's say my fitting in plot 2 had produced this pattern for my prediction for my eclipse season. Now I see I have a new moon closer to the center than my full moon is, and my new moon here is at 339.5. My apogee point is at 331.8, so it's 8 days away from the apogee point. It is 6 days away from the perigee point. So I'm still going to rate that as a likely total solar eclipse, followed by 347 to 355. That's 8 days later. A partial lunar eclipse, but possibly a total lunar eclipse. If it works out perfectly that this new moon and this full moon are each within 8 days of the center of the eclipse season, then I can get a very rare pair of a total solar eclipse and a total lunar eclipse in the same eclipse season. Okay, so that's what you want to do. Open up the spreadsheet, enter your data into the yellow cells here, being very, very careful to make sure you make no typos in the dates, following this exact date format. Digit for the month, 2 digits for the date, 20 for the year. Entering your times, being very careful to get the AM and PM correct, using just capital A, capital M, or capital P, capital M. Note that 8 p.m. is also the same thing as 2000 hours on a military clock. I can enter it that way as well. 2000 just gets automatically translated to 8 p.m. So if you're familiar with military time, you can avoid the AM PM monikers, but we're mostly familiar with AM and PM, so just be careful to type them in carefully. Type your dates in carefully. Make sure you've rounded off the dailymoonposition.com predictions of your percent illuminations carefully to the nearest 5, to the nearest round 5 or 0. And make sure that none of these values over here are that hashtag value error message. For example, if I put a period at the end of that, if I type this in poorly, P period, M period, boom, now I get a value there telling me I have a typo, and values over here and values for everything below it, so I know that something's wrong with this entry. I fix it and things go back to normal. So enter your data carefully. No matter how many moon observations you have, if you only have 5 or 6, that's fine. You can still do the assignment. Your fitting here will be more difficult, but you could start with plot number 2 and do the fit here first. And then given those numbers, transfer them up to here and then tweak them by a few tenths in either direction to make sure you have the best fit to your red data points. It's very easy to look up the day of the new moon in January. It's very easy to look up the synodic period of the moon. But I'm going to be grading you on how well your 2 numbers here produce a blue sine curve that fits your data points. Not the true accepted value, but what fits your data points. Science progresses when unexpected things happen. So if you just dogmatically follow what everyone believes to be the correct answer, you're not doing science. Science actively encourages revolutions. So you make your measurements, you fit your measurements, you trust your data. Once you have a fit to your own personal data, you predict the exact date of the March new moon. Once you've done the same fitting procedure to the class data, so let's get this 27.3, and what was this, 32? Once you've produced a good fit to the class data, something like this, where the blue sine curve is hitting almost every yellow diamond and every red data point, getting within the error bars of nearly everybody, doing a particularly good job of fitting the first 6 or 7 data points, the 3 green ones plus the first yellow and red ones there in early February, at the same time that it produces a good fit to the final yellow and red data points in late April and early May. Once you have that fit, you can predict the phase of the moon on graduation eve and then predict what kind of eclipses we're going to have and what dates those eclipses will take place in December of 2020. And if you remember from our lecture on eclipses, Christopher Columbus saved his own head, saved his own life from an Indian rebellion by being able to accurately predict a lunar eclipse. So do Christopher Columbus proud and figure out what kinds of eclipses we're going to have late in 2020. Okay, so that's the nitty-gritty of it. Once you've got your data in your spreadsheet and have your fits to your plots done, then you can go ahead and answer the questions that are in the instructions, and those questions will be a Blackboard assignment that I will get posted later this weekend. And over the next 2 weeks, and even beyond the week, this is not due now. I'm extending the submission deadline for the Moon Project to the Friday after finals week. So if you're loaded down with a lot of classwork from your other classes, take-home finals from your other classes, you can set this project aside. But if you're not, you can get it done early, whatever. But I will be available for one-on-one Zoom meetings if you'd like, where you can share your screen with me and show me your spreadsheet and your fits, and I can give you pointers and tips and help on improving your results. So that's it in a nutshell. Send me an email if you would like to, if you have a question, or if you would like to schedule a Zoom meeting on this assignment. All right. Have a good weekend, and I will be talking to you again soon.